let's talk about some more programming. So we're going to animate some more stuff, which will be fun. Last time, what we ended with was a bouncing ball, right? And that was really cool looking. Let me go and copy that back into today's stuff, because I want to talk about it a little bit more, and then we're going to change it around. So let me go to my desktop, my code from class folder, and then it was lecture 24 where we had that bounce program that we made. I'm going to copy that into a folder for today. Lecture 26 is our lecture today. So there it is. And then I'm going to open this in idle. Whee. There we go. So this is the program we had last time, and remember what it was doing? Look at this gorgeous result. Nice bouncing ball there. So we did that last time. And so we wrote all this code, and somehow it's producing animation. And I think I just mentioned briefly kind of why that's working. But like the key thing is down here, right? While true, this forever loop. Repeatedly draw me a new frame. And that draw frame function takes care of moving the turtle ever so slightly. And then just keep moving the turtle ever so slightly. That will create a new picture to show on the screen. And if you show enough pictures quickly, it looks like animation. All right. So let's talk about why that loop produces animation, because that's a little not obvious, I would say. Let's see. Do I have a normal size pen? Cool. So yeah, in theory, right? If you say this a bunch of times, while true, draw frame, while true, draw frame, one valid interpretation of that code is the program keeps trying to draw frames and it will never like even get to starting the first one. It's like trying so quickly to draw a new frame, right? So in theory, if it just keeps trying to draw frames without ever like stopping, it'll just never show anything at all, will it? So that's not happening. So that's interesting. Like, won't it show frame? It'll try to show frames so quickly that you'll never see anything, or like it starts shoving out the first frame, and then like you're ready to draw the next one, so it overwrites everything and just blanks out. Maybe it's like always clearing the screen or redrawing it, but unfortunately, or fortunately for us, that's not true. All right. So what's happening when we say draw frame? The turtle.goTo is moving the turtle ever so slightly, and this call right here takes a bit of time. And the turtle program, the turtle code that was made for us by the library writers, it draws and it creates the picture of the turtle on the screen before it ever stops, before it ever gives control back to our program, and this draw frame returns, and then like we're done and ready to draw at a new time. So this function call takes time, and it draws the entire screen of the turtle. It waits until that's all done. All right. So that's the key here. And so in general, any computer takes a little while to draw stuff. And so there is a tiny bit of time that it takes for this library call to finish and to write the new turtle to the screen. Like here's the first image. And then for a split second, while it's trying to calculate and move the turtle to here, it'll keep the first frame on the screen. So this takes a little bit of time to move the turtle to here. And it'll take, likewise, a little bit of time to move the turtle to here. This goTo call takes a little bit of time to run on our computers. And that is going to show it for as long, it'll show the previous frame for as long as it takes to redraw the turtle to the screen for that new frame. All right? And so there's an implicit amount of time being taken by this call. All right? Tiny little bit. And so that's what gives us animation. We're not really in control of it. We don't really get to say how long this frame appears on the screen. It's just as fast as our computer can write the pixels to the screen. That's pretty much it. All right? That's kind of cool. If we did, though, maybe let me call this file bounce copy so that we remember it was a new file before I forget. There. So that we remember, that it's nothing new. We've done this before. There we go. So yeah, if you did want more control over how fast the frames were being displayed, you could slow this down. You could have the turtle, you can have this draw frame function wait for a little while. You have it stop the program for a little bit. There's a time library in Python. You could say time.sleep. That asks the program to wait. Just go to sleep for 1.5 seconds, or as long as you want to keep the current frame alive. pretty much. So that's one way to do it if you want more fine-grained control over how fast your stuff is being displayed. So if I do that, import time, if I say here, time.sleep for like, I don't know, 0.1 seconds, this is going to make sure that that frame, like it's going to stop the program for 0.1 seconds. It'll make sure that at least for 0.1 seconds, that frame is being shown. But it also takes a little while to do the drawing, and so it'll be a little bit extra than on top of that. So it'll look a bit choppy now when we run it, because we're not getting a very good frame rate when I'm doing that kind of sleeping. Does that make sense? But that's the kind of control you could have if you wanted. But we're just kind of letting it draw as fast as it can. We're not taking control over that. So that's something you could do. We're kind of just letting it work as fast as it possibly can. And that gives us, at least on my laptop, it gives me this speed of animation. Maybe on your giant desktop with a faster CPU, it does it better, does it quicker. Okay, any questions about that? So that's why we get animation, more or less. I hope that made a little bit of sense. It's not obvious why that's happening. So it's worth it to have a slide about it. Let's see. Oh, this will be fun. I'm excited for this. This will be a very satisfying experiment. So what I'd like to do now is change our program a little bit to make the ball bounce, not just like with a constant speed, but pretend it's on Earth and it's bouncing with gravity. So the idea is the ball bounces, it like starts falling slowly, but it speeds up as it gets closer to the ground. That's what gravity does, right? Increases your acceleration. And then it bounces, and like it starts off slow and then it comes fast, right? And then maybe it like kind of dies off because you've taken a physics class, when you bounce a ball in real life, it's not a perfectly elastic collision, right? So that's kind of what I want to see. So like bounce, slow, fast, slow, fast, slow, fast, like you're bouncing a ball in real life and there's gravity. That's what I want to do. All right. So just to spell that out, like when you drop a ball, like if you drop a ball, right, and you don't throw it, just initially it's not really moving. But gravity picks up, and like first it starts moving a little bit slowly. Slow movement as it gets a little bit after a small amount of time has passed. But after more time has passed, it's starting to move faster. And it starts to move really fast by the time it hits the bottom, right? It's super fast by then. That's the fastest it'll ever get. That's as fast as gravity can pull it down. Super fast. So it speeds up as it's falling, right? Until it hits its terminal velocity or whatever, if there's air resistance. Have we taken a physics class? Hopefully. So yeah, that's what we're going to program today, and it's really not a lot of lines. It's really interesting how little work you have to do to get it to like look like there's gravity. But I do need to teach you a little bit of physics first to make sure we're all on the same page, because we have to model physics in our program if we want the ball to bounce like this. It's really cool though. So all right, so right now, what's going on with physics terms, right? Our ball is moving with a constant, not speed, but velocity for physicists, right? Velocity in the downward direction, velocity in the upward direction now. It's moving with a constant velocity right now, okay? And that is not what happens in real life. All right, so what should happen is the ball should speed up on its way down, like after a little bit of time. After 1 second, maybe it's gone this far when you first drop it, but wait another second, it's gone even farther. It's a bigger distance now because it's moving faster. Okay, that's the goal. So, all right, now we have to ask the question, how fast, right? The ball is speeding up as it's hitting the ground, as it's getting closer to the ground. So the question is, how fast does the ball get faster in real life? It's affected by the acceleration due to gravity. Yeah, so there is acceleration due to gravity on Earth at 9.8 meters per second towards the center of the Earth. All right, 9.8 meters per second squared. That's the units for acceleration. All right, so the ball is being pulled down with this amount of force, right? 9.8 meters per second squared. And just so that we're all on the same page, that's an acceleration, right? Velocity was your speed. That's your change in position, delta position, right? How far you've moved over time, delta position. Sorry if we hate physics. And then acceleration is your change in velocity. I cannot spell today, sorry. Acceleration is your change in velocity, so it's like a step removed. velocity. It's how fast you're getting faster. And so that's why there's a squared, meters per second squared in the equation. So what this means is every second, your ball is speeding up by 9.8 meters per second. It's speeding up by 9.8 meters per second per second. That's why it's per second squared. Okay, that's what's going on. So wait a second, your ball has this speed, 9.8 meters per second. Wait another second, it's like negative 19.6 acceleration. All right. So acceleration is supposed to affect velocity. And so that's what we're going to do. We're going to make an acceleration variable. We're going to have it affect our velocity variable. All right, so every time a frame happens, we need to let the acceleration affect our velocity. The acceleration is constant, on Earth at least. And then the velocity will change. So here's kind of the setup. Here's what we're going to model in our program. Initially, the ball is like, you're just dropping it and it has no velocity. It's not moving right now. But gravity exists 9.8 meters per second squared towards the Earth, so let's say negative direction, negative y direction, negative acceleration. Every frame, we would like this acceleration to affect our velocity. So it's going to offset our velocity by this amount. So like after, initially, on the first frame, velocity is 0. On the second frame, velocity is negative 9.8. You bring it in there. And then after another frame, the acceleration is 9.8 more. So it's like negative 19.6. Does that make sense? You just keep on having acceleration affect your velocity. That's changing every time by 9.8 meters per second every second, or every frame. We're going to have some sort of units per frame squared acceleration. It'll be a little bit weird in terms of units, but that's okay. So what we need to do is make this happen, all right? That is the goal. And then we can also have it, I think just naturally it's going to stop bouncing, which will be fun. But yeah, let me code this now. All right, are we ready? So every frame, we're going to have our acceleration affect our velocity. Right now, we only have velocity. So let's see. I'll copy all this code, new file, and I will call this bounce with gravity.py. So start with what we had. I'll close this old thing. And then this program, right, the ball had constant velocity. So where is the variable that is telling us how fast this ball is moving? We gotta go find that, right? That is your turtle offset, because that's what changes the turtle's position every frame, right? That is your velocity. That was secretly a velocity variable. Does that make sense? So let's call it that now that we know what it really is. So let's call it turtle velocity, not turtle offset. Okay? Turtle velocity. And because we're dropping the ball and we want it to be affected by gravity, the velocity will start at 0. Okay? That's the goal. That's the first velocity for the turtle. And then that's going to be affected. It's not turtle offset anymore. It's turtle velocity. So all this stuff. Every time I said turtle offset, oops, oh gosh. I'm going to say turtle velocity instead. Turtle offset. Turtle velocity. Velocity. Velocity gets moved in the other direction. So that's, I just made a variable name change, and I guess I changed this variable to 0. Let's make it back to -2. So no difference, right? I just changed the variable. It's velocity. That's really what it was. Everything still works. So that's fine. All right, now let's introduce acceleration. All right. So the initial velocity of the ball needs to be 0. We're going to pretend we're on Earth. So the initial velocity of the ball is 0, and then the acceleration needs to be some value, and we want it to take the turtle downwards in a negative y direction, so it needs to be a negative acceleration to start. Okay? Negative acceleration. Actually, it's always negative. Sorry, it's a constant in the downward direction. That's how gravity works. So let's make it like negative 9.8 is a little too big because of the way we're about to do this. Let's make it like -1. Okay? Because the units, we're going to have the acceleration change the velocity every frame. So it's not like meters per second squared. It's like the units are for this acceleration variable are like units in turtle land per frame squared. That's kind of what's going on there. So let's make it a lot smaller because it's going to happen every frame, not every second. That's a lot of frames per second, right? So let's have it be that. And then what we need to do is every frame have the acceleration change our velocity rather than keeping the velocity constant. And that's going to tell us how far to move our turtle, right? Because the turtle is moving based on his velocity, but the velocity is changing. Okay? That's the idea. So at the very beginning here, every frame, the acceleration affects the velocity, which is really cool. And so all I got to do is, all right, whatever the turtle velocity was before, this thing, have it be affected by acceleration. That's all you do, right? Turtle velocity equals whatever it was plus turtle acceleration. So like after one frame, it'll be, initially the velocity is 0, but after a frame, it'll be -1. After another frame, it'll be -2, then -3, -4, right? Until it bounces off the wall. The velocity is going to keep getting more and more negative. Okay? Does that make sense? So like the very first frame, we're going to keep repeating this. If velocity starts at 0 and acceleration is -1, here's what's going on. Acceleration is like -1, and our velocity starts at 0 every frame though. It's like, this is going to be affecting the velocity. All right, add it in. So the velocity starts at -1. So the ball moves a tiny bit and in that one frame. And then the next frame, we have the acceleration affect the velocity again. So now the velocity is -2. Does that make sense? And so it's -2 units. So the ball is moving twice as far in this frame. That's going to make it speed up if you animate it like this. Then you have it affect it for the next frame. That'll make it move 3 units this time. So it's moving a little bit more every frame, and that will correspond to a speed up. Yeah? Speed up in the downward direction at least. That's the goal. So if I run this, it's amazing what's about to happen. Oh shoot, velocity is not defined. Where did I say velocity rather than turtle velocity? Sorry, it's turtle velocity. The suspense, I know. There we go. Boop. Look at it. It's bouncing, and then it's actually getting slower and slower and slower. It's taking a little while, so it's kind of choppy. That was really cool. Let's change it to have a slower acceleration, -0.5, let's say. Maybe that will display better on my screen. Whee! Look at it. It's bouncing. It's speeding up as it's getting closer to the ground. And then it's actually losing height as well, which is really cool, just by the way we made it. And then it just comes to a complete stop. So we just introduced gravity, which is really cool, with one line, pretty much. Are there any questions about that? It's amazing. And the ball is coming to a stop because of a weird fact. Let's see. How do I want to do that? The ball is coming to a stop for a weird reason. Let me try and explain. Because normally you'd think it would just shoot off back up towards the top. Here's what's going on there. Because of the way we bounce, like the code that we use to bounce off the walls, it is very possible that when we notice we're like at the bottom wall, we're never going to hit the top wall anymore. When we notice we're at the bottom wall, sometimes we have to like move the turtle back inside if you went a little bit too far. Like he was trying to go down here, right? If he was trying to go down here, we have to move him back up to just be touching and then shoot off his velocity in the opposite direction. Because of that, we lose a little bit of force every time. We lose a little bit of velocity because like he would have gone farther, but we moved him back up. So that's the problem. You're never gonna like you're gonna lose a little bit of velocity because we like move the turtle back up at the start there. So he wasn't able to get to the maximum speed that he could have gotten to if like he hit exactly the bottom there. If that makes any sense at all. So one thing you can do if you hit the bottom, if you want this to be a perfectly elastic collision and always bounce up straight back to where you came, if you like print out like what was the highest velocity here, right before we change, print turtle velocity. Let's print the turtle velocity every time we bounce off the wall. So it looks like the highest point, the first time it was 19, and then it was losing velocity by 0.5 every time. Okay, so if you just shoot it off with a 19, positive 19 velocity, then it will be a perfectly elastic collision, if you want to do it that way. So let's see. If you do, instead of this, if you say turtle velocity, and this depends on your acceleration choice, by the way. If you make it, if you hard code it to be 19, apparently, that's what it wanted here. All right. So this creates a perfectly elastic collision by hard coding the new acceleration. Because then it'll always be that acceleration once it bounces off the bottom wall. And so it'll always go back up to the highest point, again, the tippy top of it, where it started. It will never lose speed. Whee! So then it bounces right back up, and it will never, we're shooting it back off with the same velocity. Every time it hits the bottom, it's never losing velocity. Okay? So I hope that made a little bit of sense. But honestly, all that we needed to do to produce gravity was make a variable for it, and then just have it affect your velocity. That was the one line. This was the real meaty line. It's the only thing you needed to add, and suddenly we have modeled gravity in real life. I think that's really cool. All right. Sorry if it's been a while since you've taken a physics class, but hopefully that made at least a little bit of sense. Are there any questions about that? Oh, that's the acceleration. Because I'm having the acceleration affect the velocity every frame, so the units are really weird. So it's like go down half a unit. Tell the turtle to increase its speed by half a unit in the downward direction every frame. Yeah. And so if we make this larger or smaller, it will change how fast this turtle speeds up. So you make it huge, then it'll fall very, very fast. It's like you're on a planet with a lot of gravity, like Jupiter or something. So I encourage you to try that. You'll have to change this. Maybe you'll have to put this line back to how it was. But that would be fun to play around with, I think. Yeah, any other questions? All right, so that's a fun program to study, I think. Now, if we are happy, I have another thing that I want to show you. The next goal is to go back to constant velocity, but introduce a second dimension. So have we all seen this Office episode where there's the little DVD menu and it's like bouncing off the corners? I'm going to play that for us just so that we're all on the same page, but we're going to make this, all right? I do have to stop the recording, have to pause it for a second, because if I play this copyrighted thing, I'll get they'll take my YouTube channel away. All right, and we're recording again. So that's what we're going to do. We are going to, instead of having the ball like bounce up and down in one axis, we're going to introduce a second axis and make it a square. We're going to give it like a random starting direction, then it'll just start bouncing. It'll be like, whee, bounce off the corner, bounce off here, go this way, bounce off this way. Bounce in the way that you expect it to bounce. Whee. And so just keep on doing that all day long, and maybe eventually it will hit the corner. So that's what we're going to program. All right. Not today though. We're just gonna we're gonna plan it today, and then we're gonna do it next programming lecture. All right. So let's try and write down all the things we need to do to make this happen. All right. Because we know a little bit. We know how to move it in one axis. It's really just a bit of an extrapolation from all that. It's not too horrible. So again, we need to draw the screen boundaries, which we know how to do already. We just call our little draw rectangle function. We'll draw that little square. And then we want to create a square, not a circle, in a random location. Could be any XY coordinate. Could be over here. Could be maybe over here. Doesn't matter. So that's the goal. We got to start a square off, not a circle off, in a random spot. Somewhere in the middle, maybe. So we'll need the random library for that. And we don't have to be like touching the top or the bottom. bottom or anything. Just like somewhere within this bound, put a square. And of course, we're going to make the turtle the square again, but that's beside the point right now. So that's what we do. And then, like, he's got a random spot, and his coordinates are always relative to where his center is. And then we're going to give that square a random direction. That's going to be the new thing that we have to figure out how to do. A random direction, like, all right, randomly choose that you're going to go that way, Mr. Square. Okay? And then, all right, once we've chosen that, once we know what direction it wants to move in, and we know where it starts, what do we have to do? Maybe we're not really sure about how to do any of that, but like at a high level, what needs to happen? We need to move in our current direction, right? Every frame we move a little bit in our current direction because that's going to produce animation. And so like maybe next frame, the square ends up here. Boop. Yeah. And then maybe the frame after that, the square ends up here. So we're moving in that same direction until we hit a wall. All right. If there's nothing in our way, keep moving in that direction. Until we hit a wall, and that's the same as just the bouncing ball, just moving a little bit, but we have to worry about like changing our x and our y now. It's no longer just up and down, right? No longer just y. We're moving a little bit to the left and a little bit up, yeah? That's what we're going to do. We have a second axis, and then if we ever hit a wall, we have to come up with some if statements to like bounce off of that. So like, all right, if we're coming this way, we got to bounce off that way. You have to figure out how to represent that in code, but once we have that, it's just, well, that's another direction. Move the box by that much. And eventually it'll hit this wall, right? It'll hit this wall, and it'll bounce off in that direction. Something like that. That's going to be what we do. Does that game plan make enough sense? Not that we know how to code it yet, but do all those steps make enough sense? Have to figure out how to write the code for all of those steps. And once we have that, we have our animation. All right, if we are good with that, let's try and zoom into some of those ideas and see what we got to do. All right, so we will make the turtle the square again. That's fine. And then we'll be able to use his coordinates. We can just give him some random x and y coordinates, and that'll start him out somewhere within these bounds, which is great. That's fine. So just tell the turtle to be a square rather than a circle, because we did that here, right? We made the turtle shape a circle. We can make the turtle shape I think it's a square or a rectangle. I can't remember. One of the two. We'll find it in the documentation. And then we just tell him to go to some random xy coordinate within the bounds of this outer window. And then he has coordinates relative to a center that we can go and use. All right, and then we have to figure out the hardest problem is how do we figure out how to store a direction? Like I want the square to move that way, in that weird diagonal direction. Like it could be anywhere, right? It could be that way, it could be that way, it could be that way. Especially when it bounces, it could go any direction, right? So we have to be able to represent all of them. And so how do we do that? All right, every frame we want to move the turtle in that direction. How do you represent that direction? All right. It's like, let me draw this out. You might understand it as I draw it. So like, all right, my direction is that way. I want to move every frame by this amount. So the next frame, let me make that a little bit bigger. The next frame, the turtle center should be here, and then the square should be drawn like this. All right. So every frame I want to go that way. Change the coordinates to be there. Does anybody see how you might be able to do that? So before, when we were moving straight up and down, we had an offset for our y, right? Offset for our y. Move a little bit up, move a little bit down. Change your y by that amount. The same game applies in 2 dimensions, in fact. We can again store the direction, even if it's a 2-dimensional direction. It's just this time we're going to use multiple offsets. We're going to need 2 offsets because every frame we move a little bit in the x direction. Does that make sense? Move a little bit that way in the x direction, that's delta x. And then we move a little bit in the y direction, either up or down, right? And that's our delta y. So that's how we can represent our directions. Does everybody see that? Does that make enough sense? So instead of just like, it's before our velocity our velocity was a delta y. It was always change your y amount by a little bit. That sends you straight up or down. But now it's delta x and delta y. So go left or right a little bit, and then also go up or down a little bit. That'll give you diagonal movement. Do we see that? That's the goal. And so with enough, like maybe this is this offset is like go 3 in the positive x direction. So delta x is 3 and delta y is 2. Go up in the, it's more like 1 honestly, go up by 1 every time. And so, yeah, every time you move your square, this is how it's going to move, right? It starts, let's say it starts at 1, 1. The next frame we want to move by this, in this direction, which is move x by 3, move y by 1. How do we have that affect our position? Well, again, we're just going to do this. We're going to draw our little, we're just going to have it affect our position, just like this. We're going to have it move to whatever its original x was plus delta x. It's like, all right, it was 1. We're going to add delta x to that for the next round. And then it was 1 for the y. We're going to add delta y to that for the new round. So it was at 1, 1, and so it's going to be now at 4, 2. Do we see that? Now it's going to be at 4, 2 the next round. That will exactly move it in that direction. All right? And then the next round, the next frame, it's like we went left by 3, up by 1. If we do that again, left by 3, up by, or sorry, right by 3, up by 1. The 4, 2 will turn into what? 7, 3, yeah? So this is 7, 3. That's the idea, okay? That's what's going on, and that's how it is being offset. And so do we see how we can use 2 offset values, change in x and change in y, to represent a diagonal direction? All right, we just need 2 now, 2 of them. So every kind of direction that you could ever hope to have has an associated offset, an associated xy offset. So here's the idea, like, all right, you want to move straight this way, it's like, I don't know, that's like 1, 1. This is change in x by 1, change in y by 0. This is change in x by 1, change in y by -1, etc., etc. Any direction you might want to move, there is an associated x and y offset for any of those, okay? And I'm sure you can come up with them. Just draw the little triangle, like how much did we move this way, how much did we move up? Sometimes it's negative for x, sometimes it's positive, and vice versa for y. It's all the same. So every direction has an offset. One thing that we are going to have to worry about when we pick our random direction, we kind of want the turtle to always move at the same speed. So it would be nice if this arrow, this direction arrow that we pick, always has the same length, no matter the random direction we pick. So like, I think you can imagine, like, if I pick this direction or this direction arrow, it's the same direction that you're moving, but like this arrow will send the square in that direction faster than the other one. Do you see that? So it would be nice to like always, regardless of the direction that we pick, just to have it be normalized. That's the fancy term. Normalize it to make sure that this arrow is always like length 1 or something. That's the goal. So we're gonna have to worry about that, but that's a job for next time, right? But I think the goal of this slide was to tell you how we can represent 2-dimensional movement with an x offset and a y offset. All right. So every frame we're going to have the box be affected by that x offset and that y offset, assuming we're not hitting a wall yet. Okay? Any questions about that? Because that's it's getting closer and closer to being implementable. We can do it. Maybe you can try it before we get to it next time. See if you can get it before we. There's that. So if we're good with that, let's talk about how to bounce off a wall, because that's the other hard part. We kind of did this already, right? It's like these kinds of if statements, like if we hit the bottom wall, if we hit the top wall, we have to like move, change the way that we're moving, change our direction a little bit. And so we'll have to worry about that again here, all right? So in our example, in the square that we're going to draw, it's a 400 by 400 square that's centered at 0, 0. So like, let me set the scene and draw the bounds. This is what we're going to be working with. So 0, 0 is in the center here. And so all these lines are the bounding lines of our arena where we can move this little square. So what are all these lines? What are their equations? So that'll tell us something. So this down here is the y equals negative 200 line. This up here is the y equals positive 200 line. this left side is x equals negative 200, and this line is x equals positive 200. All right. So if we look at our coordinates of our box, we can notice when it's hitting the wall or if it's trying to go outside of it. All right. So in this example, the turtle, we know that the turtle has hit the left wall. Like if it's moving this way, we know that it's going to hit the left wall when, let's not worry about like the, what's it called? Let's not worry too much about like it trying to go outside right now. But the turtle's moving that way. We know it's hit this left wall essentially when the x coordinate is trying to become smaller than negative 200, or it's equal to it. Okay? If it's equal to it, it's like grazing the wall. If it's trying to be even smaller than that, it's trying to move outside of it. Does that make sense? So once we know we're at the left wall, when this x coordinate is small, when it's about negative 200, all right? We do have to worry about the width of the square because the coordinates are relative to its center, so we'll have to deal with that, but just pretend it's exactly negative 200 is when it hits the wall for right now, all right? So that's something we'll have to check for in an if statement, okay? Just like we checked for hitting the top wall like this and the bottom wall like this. Actually, we can keep those, in fact. That's totally fine. So similar fact exists for the right wall. Like if the x coordinate gets huge, if it's over here, we know we've hit the right wall when the x coordinate of this square is like 200. You see that? Or it's trying to go outside if it's bigger than that. So that's another if statement. Okay? And then we have the same going on for the top and the bottom walls, which we've already dealt with. Like we know that the turtle has hit the top wall. It's somewhere along the top wall, one of these places, right? When the y is about 200. Or trying to exceed 200. And same with the bottom wall. We know that the turtle's somewhere down here if the y is negative 200. We don't know how far it is to the left or right, but we know it's at the bottom wall. Or it's trying to go outside of the wall if it's less than that. Okay? Any questions about that? Because that's how we're going to notice if we've hit a wall. Right? Now we have to figure out how to bounce off. Okay? So let's pretend we have hit, let's pretend that our direction is this way. So we've got some associated x offset and y offset for our turtle, for our box. And like here's the top wall, we're getting close. And so we're trying to move this way, and then we hit the top wall. All right? Which direction should we bounce off? We're coming in this way. Does everybody see that it's that way? That's the direction we want to move off in. We're coming in this way. Bounce off in that direction. And so how do we calculate that direction is the question now. So this is the new direction arrow. And if I draw this properly, there should be a 90-degree angle here. So that's how you know your new direction, more or less. Like this should be a 90-degree angle right there. Okay? So based on our previous direction triangle, what should the new direction triangle look like? We should be moving downwards a lot. Not upwards, but downwards, but same delta x, right? So we draw we draw the triangle. We have a new delta x, right? Or we have the delta x. That's still the same amount, right? Still move right. Still keep moving right. Positive x direction. But instead of moving up in the y direction, now we're moving down. Do you see how that's flipping? Just the y direction. So this becomes whatever delta y was before, but negated. That turns into our new direction. Does that make sense? This was a positive x, positive y direction, but we hit the wall. We want to bounce off this way. And so we want to keep the same positive x. Keep moving to the right a little bit every frame, but move down now. So take the y and negate it. Okay? So negate the y offset if we hit the top or the bottom walls. A similar fact exists for the bottom wall, of course. And then if we hit a left or right wall, we're going to negate the x offset. Let me try and draw that. Very small. Let's say that we're coming in this way. Boop. And here's our square. We were coming in with a delta x and a delta y. Delta x, delta y. Sorry, it's very small. Delta y. And then we want to bounce off this way, right? Which is going to be same delta y. Keep moving upwards. Keep moving upwards when you hit a left or right wall. But instead of coming into the left and up, now you're going right and up. You see that? Now it's right and up. So the x offset got negated. All right, so if we hit a left or right wall, we negate our x offset. If we hit a top or bottom wall, we negate our y offset. Does that make enough sense? That's going to be the key here. All right. So if we hit a side wall, it's the x offset that needs to change because we were coming into the left maybe. Now we need to come out to the right. Same y offset. Keep moving up or down. We didn't hit one of those walls. And then for the up or down direction, we negate the y offset for the top or bottom walls because we were coming upwards and we went too far up, so we need to go down. Keep the same movement to the left or to the right. We didn't hit the side wall, but go down instead of up now, or up instead of down. Okay, that's the goal. It is possible to hit the corner when you're coming at both. In that case, you're going to have to flip-flop both your x and your y. You'll just have two if statements that just do both at the same time, right? One after the other. That will just fall out of the way that we write this because we'll just have a bunch of if statements and multiple of them can fire at once. All right, that's going to be our goal. So sorry if that's a little confusing right now because we're not going to code today. We're just trying to plan out everything first. But let me try and make a drawing of how this needs to work with actual coordinates involved, and I hope that should help. So here is, let's zoom in, here's the left wall. Here's the left wall, and here is our turtle. Here's our square. It's moving towards that left wall, all right? So our direction is this. Let's say that our direction is go left 2, so negative 2x offset, and go up 3 every frame, positive 3 y offset. So if this was our coordinate, if it was negative, let's say negative 198, 2, then the next frame, we're moving this way, right? 2, 3, we will be hitting that sidewall. We'll be right here. Let's say. Whee. Doing that. And so that sends us to, what is this coordinate? It is going to be, well, negative 2 plus the x, right? So negative 200. And then 2 plus the 3, so 5. So that's where we move in the next frame, and then we notice we hit the wall, and so we have to offset our direction. Instead of going in this way, we want to bounce off that way. Does that make sense? And so what is that? That was, well, we're bouncing off to the right and up now. It was keep our same y offset. We're still moving upwards. Keep the same 3 there. But instead of moving left and doing that, we're moving right and doing it. So it's positive 2. Does that make sense? That's how you bounce off on the left wall. So we're going over by 2, up by 3 this time. So there's a 2 there and a 3 here. And so the new coordinate of our square, which I don't think I drew this too accurately, that's good enough, should be negative 200 plus 2. So we're back at 198, negative 198. And then we're still going upwards. So it's 5 plus 3, so 8. That's our new direction, or that's our new position after that second frame has drawn to the screen. All right? Does that kind of make sense how we're going to use these directions up until we hit a wall? Then we're going to negate one of the sides of it to make sure that we bounce off in the correct way. We don't exceed the bounds of our playground here. So before we were going left by 2, negative 2 in the x, and then up by 3, then bouncing off the wall. It goes that way. So it's going to be 2 in the positive x direction, up by 3. Yeah, so I think that's about as good of an explanation as I can give you right now before we code it. Are there any questions about any of that? So next time we're going to make this bouncing box, and it's going to be really cool, and I think we have planned out every little feature that we needed. It should work out. Alright, so if we are happy with that, I think that's all of the lecture that I want to give you today. That's the programming lecture. And we have a new programming assignment to release. This one will be due week 16. Alright. So, let's see. What are we doing? So 2 weeks from now, it will be due. And then, eventually it will load. It's sure taking its sweet time, though. Let me try refreshing. That's really unhappy. Try again. Well, sorry you have to wait in suspense of all this. Does Canvas just not work right now? I wonder if my click to make it available didn't work either. There it goes. Yeah, it definitely didn't publish. There we go. So now it's published. So cool. It's there now. So here is my problem for you. All right. I would like you to not, you don't have to like do the 2D bouncing that we just did, but take our old bounce off the walls with constant speed program, this one. So start here with our bounce program from last time. So just this one with the constant velocity. Start with this program. You'll steal that from my code from class. And what I want you to do with it is the following, all right? You're going to have the ball bounce, and we're going to pretend that every time we hit the wall, something magic happens. The walls are made of magic, all right? So using turtle and random, do the following. You're going to do most of what I've done, right? Draw the bounding square for the walls, make an animated ball bounce up and down. So you'll just steal all my code from that. So I've done those first two things for you. And then what I want you to do is randomly make something weird happen every time the ball hits one of the walls. All right, so you're going to have to hook into that code where you notice you hit the wall and do something weird randomly each time. All right, so here are some random things if you're out of ideas. Here's some potential things you can do every time you hit the wall to make the wall seem like it's magical. All right, so you can change the color of the ball to be randomly different. You can change the size of the ball, like, I don't know, change it to be like tiny to large between those offsets. If you want a floating point value that's random, you have to do random.uniform, not random.randint. So we have to look into that if you want to float rather than an int. You can change the x coordinate of the ball to a random one within the screen, like have it teleport every time it hits the wall. You can change the speed of the ball. We know what variable that is now by some random factor. Speed it up or slow it down. You could also change the shape of the turtle to be like not a circle anymore. Make it a turtle. Make it a square. So here's what it should look like. Every time it hits a wall, it does something random. So it changed to a square. It changed the speed. It changed the color. So every time you pick some random thing to do, change the color, change the speed again randomly, change the shape. So something like that. And then it teleported. So that's kind of what you're going to do. Does that make sense? That's your random stuff. Every time you hit a wall, do something random. Now change the size, change the speed. So that is me trying all that stuff out. So that's kind of what it should look like when you run it. And here's what I want you to do in order to make that happen. I'd like you to make a new function called do something weird, all right, or some other similar name to that. And you're going to call that whenever you hit a wall. All right, so this is me forcing you to write functions and practice functions. And so you're going to randomly pick what to do inside of that function. So every time your ball hits a wall, pick from something random and like be like, all right, I'm going to change the color this time, or all right, I'm going to change the speed this time. You should have programmed at least 3 different weird things to choose from. Like you flip a 3-sided coin every time you hit this function, and you pick one of those at least 3 things to do, and then you go and you do it. Like, all right, this time I'm going to change the shape randomly. All right, but you pick it randomly every time. You're just flipping a 3-sided coin or picking a random number. But that's where I want you to put this code in a new function. Okay? Any questions about that? So you'll call that function every time you hit the wall. Yeah. Every time you hit a wall, you do one thing, but you should have pre-programmed 3 potential things to do. So you'll choose a random thing to do each time. Does that make sense? Yeah. So you don't do like 3 random things every time you hit a wall, but just like have 3 things ready to choose from every time you hit a wall. Yeah, and you'll randomly pick one of those options. So like, oh gosh, here it starts over again. So every time you hit a wall, it's doing one random thing, but it's choosing from like 5 different random things. So there it randomly just changed the shape only. Randomly just changed the speed only. Randomly just changed the color only. But all of those were programmed and ready to be chosen from. Okay? That's the goal. So this is me forcing you to make a function. So just call this function every time you hit a wall, and then work on that. Okay? So that's the goal there. Any other questions about that? So it's a little bit involved, but once you get the setup, it shouldn't be too bad. Definitely ask me questions if you have them. Here's my hint for you on how to choose between random things. So let's pretend that you've programmed, or you want to think about doing 5 different weird things. Every time you hit a wall, you're going to choose one of those, one of the 5. So here's a way to pick something randomly. So what you'll do is you can just pick a number between 1 and 5, if you have 5 things to choose from, and just call that a variable, set it into like an n variable, and then use a big long if-elif to figure out which value n was and became randomly, right? Because it's either 1, 2, 3, 4, or 5. It was randomly chosen. So if it's a 1, do your first weird thing. If it was a 2, do your second weird thing. That's how you can choose among the options that you've programmed. Does that make sense? That's how you can do that. It's probably the easiest way. So yeah, that's what I want to see, something like this. You only have to do up to, at a minimum, 3 random things, but if you want to do it cool like that, you could. Now you know. All right. I think that is all that I wanted to say. So you got 2 weeks. Definitely start early. It's a little weird to wrap your mind around, but you can steal most of my code for the first step. All right. If we are happy with that, that is all that I have for us today. You have time to get started.